Hello everyone, welcome to Stochastic Calculus for Finance 1. This is section 4 or chapter 4 on American derivatives. So we'll first talk about the introduction about what we want to talk here about. First we will study the difference between European and American options, and this is fairly simple. As you know, for European option, it can be exercised only at a specific point in time, right? At a specific date. Well, like the American option is very similar to a European option, but with the American option, you have the possibility to exercise the option anytime between now and maturity. So, because the American option has like the special possibility that you have, that extra capability, then you can say the American option has something called an early exercise premium over the European option. And because of that, basically, the American price, the price of an American option is at least as great as the price of a European option. And there's also another concept of intrinsic value that we need to think of, especially with American option. And what that means is that the American price, the price of an American option at any point in time should be at least as great as the value you will get from the option if you were to exercise it today, right? And that value that if you exercise the option today is called an intrinsic price or intrinsic value. And we have seen this before. If you consider this process, the European discounted price process, right? We have seen that that's a martingale. However, we will see that with American option, if you consider the American discounted price process, this is actually a super martingale. And by super martingale, what we mean is the price of the American option tends to go down as time passes by, right? And that is because it tends to go down because the owner of the American option may fail to exercise the option at the optimal time. And that's why it would be a super martingale. And for pricing, the way we're going to do this, if you want to think about pricing American option, we can imagine that we sold the option for an initial amount, and that we use the initial amount that we sold the option for to build a portfolio by trading in the underlying and the money market to hedge that option. And so the portfolio that we're going to build, we need to make sure that at any point in time, it will allow us to pay basically the option owner whenever they exercise the price. So we need to make sure that our replicating portfolio is always as great as the intrinsic value of the option, of the American option. And to do that, we're imagining that we're selling the option to a guy that's very smart, and that guy is going to always exercise the option at the optimal time. And so to really be able to handle that the concept of basically the option can be exercised at any point in time, and it's exercised at the optimal time, we're going to introduce the concept of stopping time. That would be like a construct that will help us really think about this possibility of this option getting exercised at any point in time. All right, so let's move to section 4.2. where here we just first look into non-path dependent American derivatives. And to do that, we'll just have a quick review of European derivative pricing algorithm. And we have seen this in the previous videos. So consider a derivative security that payoff an amount Gn at maturity. And so this Gn is a function, the payoff function. So we know that the stock price is Markov's. So really at any point in time, the value of like basically the option can be written as some function of the stock price as we see it today. And obviously if n is like the n, like whenever the option is maturing, then the value will be just basically gs, which is basically the payoff function. And at any point in time before maturity, then since we know that the stock price, the discounted price is a martingale, so we can kind of use this risk neutral pricing function that we have seen here, and we have seen this also before in the previous videos, so nothing really new here. And to build the portfolio that will replicate the European option, we can basically use this relationship that again we have seen, that quickly would able us to know how much stock do we need to hold at each point in time, and consequently how much we need to invest in the money market. And so this is just like a quick picture. So we have the stock price, and this is like a 1, 2, 3 period, let's say, all right? And this binomial model here is basically consistent with these parameters Then you need to find the price of this option. We just really need to say, okay, at maturity, we always know the price at this point. We just use basically the payoff function, right? The payoff function. So then when you find the price at this node, then we just use basically recursively the natural pricing formula to really find the price at this node, and do the same thing to find the price at this node always as well. And once we do that, then we also know the price at each of these nodes. Then we can use again the same natural pricing formula to find the price at this node, and this is basically V0, the price of the option if you were to price it today. So that's what this European derivative pricing algo is telling us. So how can we move from there to talk about American pricing algo? So again, remember how we're pricing the American option. We're really trying to use pricing using no arbitrage. We imagine we sell the option, and we use the proceed from selling the option to build the replicating portfolio by trading in the money market and the underlying asset, right? And so this is what I have here. So let's imagine that the option has a payoff basically of GSN, and it can be exercised at any time n, right? And the replicating portfolio XN must always satisfy basically this relation, right? And what this is telling us is basically the price of the option, the value of our replicating portfolio at any point in time n must be greater than or equal, like the amount of money that the owner of the option should get if they exercise the option at that given point in time. And so basically the European algo then will simply be modified just like this slowly. So at maturity, the payoff will be given by this amount. Obviously, you will never exercise the option if you're going to lose money on it. So really, like, the worst case scenario is you don't exercise the option and you get $0. And then at any other point in time in between, this is basically the price of that we have seen in the European option if using the reasonable trap pricing. And GS here is now basically becoming the new floor instead of 0. So what this new floor means is that the value of this option really can never be less than the intrinsic value, how much I get if I exercise the option today. And the replicating portfolio process, you can use this to find how many, at any point in time, how many of the stock you need to hold. And that's given here, and we will see more of that. So let's look at a quick example to see how this can be used. So as a reminder, this is like basically the recursive algorithm we're going to use to price these American derivatives. And this is basically what we use to try to figure out how many of the stock we need to hold at each point in time. And let's imagine that the portfolio process is defined this way, right? So at any point in time, if at time n I had delta n shares of the stock, then when we move at time n plus 1, of course the value of my stock portfolio will be the number of shares that we have multiplied by the value of one share of the stock, right? And then so we started. This is how much we had at the beginning. This is how much we used to buy the stock at time n. This is how much money you spent to buy the stock, and maybe I was able to consume some, right? And that's what this amount is here. So this is how much will be left in my bank account, and since it's in the bank account, it's going to grow at the time. It's going to be invested at the rate of R, and so when I move at the next period at time n plus 1, obviously this is what I'm going to have, right? It's the cash that I have grows at the interest rates in the bank. And okay, so let's use these parameters as basically the parameters to build a tree. And with these parameters, the risk neutral probabilities of going up or down are all equal to 0.5. And we imagine the payoff of basically this derivative, this American option that we're going to try to price here is given by this. So what this means is basically the option is a put, right? It's a put because basically whenever the value of the stock is less than 5, then we can make money out of it. Okay, so the tree, we build the tree here. And so using this this algorithm, we'll find like this is going to be how we're going to price this option. So let's see how this is built. So basically we can see where this 0 is coming from fairly easily. So at time, if you get to two tails HH, so the value of the stock is 16, right? So 5 minus 16 is negative. So of course you're not going to exercise the option when you are at this node. So the value of the option at this node is 0. The payoff is 0. And at this node, again, we see the stock price is 4. The strike price is 5. It's a put. So 5 minus 4 is 1. So that's where this one is coming from. And this 4, the stock price is actually 1. So when I use the same, then 5 minus 1 would be basically 5 minus. Am I really thinking about 5 minus 1? Well, 5 minus 1 is 4, so that's where this is coming from. So this is basically where the math is coming from, right? So using this, we know really like the prices. We know the value at each of these nodes here. Then we just use basically the algorithm to find the price at this node here. So where this 0.4 is coming from, again, is very simple. At this node, the value of the option is 8, so we just fit 8 inside this function, and we find that's right 5 minus 8 and all this stuff, and we'll find that basically 5 minus 8 is negative, right? So that means we just need to look at this value here, and that's 0.4, and we do the same thing here as well. Yeah, there's actually a bug here, so this should actually be 2 instead of 8, and we find like basically 5 minus 2 is 3, which is bigger than whatever amount is here. Hence, like the value of this at this node is going to be this, and then we apply again the same formula to find the value of the American derivative today. Okay, so this is how basically we can use this to find the value of the American, and then we can really try to find now how will we build the replicating portfolio. So the replicating portfolio will be given by this, and of course, like at any point in time, we can make sure that the value of the replicating portfolio is equal to the value of like basically the option, right? So we sell the option for 136, and we get 136. That's like the initial wealth. And with this proceed, now we need to build the replicating portfolio. So first we need to find, okay, at time 0, how much of the option of the stock do I need to hold? And we see that using basically the formula here, we see that, oh, okay, I need to really short 0.43 share of the stock. Okay, so when we do that, then we can make sure that whatever we have tail or head in the next coin toss, is whether it's tail or head, then we'll have enough to really hedge this the option. And we have seen this in many other videos as well, so I'm not going to go to the details, but something is special here. So imagine basically the first coin toss is a tail, right? So if the first coin toss is a tail, so that means like basically the stock price went down to $2. So the option is actually in the money, right? Because the strike price is 5, the stock price is 2. So really, the intrinsic value, if the owner exercises the option right away, they can get $3 from us. So if the agent actually exercises the option, then the value of our portfolio would be 3, right? And so we can really take like basically just sell up our portfolio, get the $3, and then give it to the owner of the option. And that's what we do. We sell the portfolio and then pay the $3, and we're done. There's no need to hedge further. But imagine for example that the stock price went down to 2, but then the owner of the option actually did not exercise the option, right? So if you come here and the owner didn't actually exercise the option, so that means we can really not start worrying about this this GS here, right, which is $3, right? So to find like how much now we need to exercise, given that we know that he's not exercising the option, then we know the value at this node, then we can just use basically this side of the equation to find like how much we need to how much do we need our portfolio to be valued today to really like hedge for an option that can be $1 tomorrow or $4 today, given that we know it's not gonna be exercised today, no, for sure. And for that, then we can just use this formula, right, which is we just discount the value in the up, the value in the down scenarios, and each, like, you know, the probability of those, and you find $2. So notice what's happening here now, right? So we need $2 really to hedge. We need the value of our portfolio to be $2 to hedge if the guy is not going to exercise the option when we get a tail. But the value of our portfolio is actually $3, right? So the beautiful thing that's happening is that we can actually consume $1. We have $3, our portfolio worth $3, but really we need only $2 to hedge basically the next scenario. So that means we can consume $1 for free. So what happened here is that basically the owner of the option really missed like an opportunity to let like an opportunity to exercise at the optimal time pass by, and because they failed to exercise the option at the optimal time, then we get like basically a free $1 in our pocket, which is nice. Okay, so here we just basically the theorem that kind of like just reiterate everything we have seen so far. So if we consider we are like in the end period binomial model, if we were like end period binomial model, and the payoff function is given by GS, then the recursive function backward in time, like, so we just need to find this recursive function Vn minus up to V0. It is defined by the American algo, and we have seen how this is done. So that at maturity, then we just say like how much do I get if I exercise the option today, and does it worth it? If it doesn't worth it, then I just don't exercise. At any point in time before, I just need to make sure that the minimum that the value of the option can be is its intrinsic value, and the value of the option basically the value of the option in the next 2 time period discounted to the present, weighted by the recent time probability of default, recent time probabilities. And we have seen how this is done also. This is just a recent time pricing formula. And then we can define basically this delta n, which is going to be basically guiding us and figure out how many of the stock do we need to hold. And there's also, we might have a chance to consume to if basically the discounted the value of the option at time n is at the time today is less than basically the price of the option if we were using the recent time pricing. Then the difference here means like we can have the opportunity to consume an amount called Cn. And once you have this, then if we start with x0, which is equal to v0 s0, the price of the option today, so we can use this really to build the portfolio process, and the portfolio process will follow basically just this strategy, right? So I just consider how much of the stock I had at the beginning, and at time n the stock price will move from Sn to Sn plus 1. So this is basically the value of my stock holding, and then there's like a certain amount of cash that was invested in the in the money market. So the amount that was invested in the money market will be the amount of wealth that I start with, xn, and then from this xn I spent some money to buy the stocks, right? So basically this amount will be the amount of money I'm left with after I buy the stock, and then maybe I consume some cash as well, and then so this whole thing will be basically the amount of money I'm left off after I buy the stock and after I consume Cn, and that amount that I'm left off with will be invested in the bank, which will grow at 1 plus r once I arrive at time n plus 1. And that's all there is to it really. And then if the portfolio process follow this, then you will notice like every point in time, like the value of our portfolio will be equal to the value of the option, right? And in particular, the value of our portfolio will be greater than or equal to the intrinsic value of the option, in case the option is exercised at any point in time. And that's why this replicating portfolio will work. All right, thank you very much for watching, and see you in the next video where we'll be talking about stopping times. If you like this video, guys, please feel free to subscribe. Let me know that you help someone out there that I'm putting this video, and also give me some encouragement to keep doing this. Thank you very much, and bye bye.